So next we have is B, and it's for beta blockers, or the proper name is beta adrenergic antagonists. Now the mechanism of action is unclear, but the response develops slowly. Now there are many types of beta receptors, just as there are many alpha receptors in the body, all which can cause different effects, such as some can cause constriction, some receptors can cause relaxation at the end. Now what beta blockers aim to do is block the action of the receptors which cause the contraction, and the ones that increases blood pressure. For an example, here is the cell membrane of the heart, the myocytes, the muscle cells of the heart, which have beta type 1 and beta type 2 receptors, mostly beta type 1 receptors. When noradrenaline binds, it works through a G protein mechanism, converting ATP into cyclic AMP. Cyclic AMP then follows other reactions within the cell, but basically finally leads to an increase in cardiac output and muscle contraction, all which increases blood pressure. And this usually occurs through an influx and accumulation of calcium ion. Now it should be noted that beta blockers not be taken with people who suffer from pulmonary complications, such as asthma. Now this is due to the beta type 2 receptors found in the lungs, which usually cause relaxation, not constriction, relaxation. So if the beta blockers were taken, the lungs could not relax, which means that it would go in a hypertensive state, leading to more serious pulmonary complications. Now we will look at these different types of receptors in more detail. So here we have the cell membrane of various organs who have beta receptors, such as the eyes, the heart, the kidneys, the lungs, and there are many types of receptors. There's beta type 1, beta type 2, beta type 3, beta type 4 receptors. But there are mainly two. There's mainly beta type 1 and beta type 2 receptors. And they are found in varying amounts in each organ, such as there's more beta type 1s in this organ, and there's more beta type 2 receptors in this organ. For example, in the heart, beta type 1 is mostly found, then beta type 2. But there are still beta type 2 receptors in the heart, of course, just not as much. And now, also the eyes and the kidneys also have mostly beta type 1 receptors. And again, there is still beta type 2 receptors on them, just not as much. Now, beta type 2 receptors are mostly found in different organs, such as the lungs, smooth muscles, and uterine muscles. And these beta type 2 receptors usually cause relaxation. So you can see why taking beta blockers can cause severe lung hypertension, because the beta type 2 receptors can't cause relaxation properly when taking beta blockers. Now beta blockers block the beta receptors, as mentioned, which aim to decrease blood pressure. Now they usually end in LOL, lol, or olol, such as one is propanolol. Now this drug is a non-selective drug. What non-selective means is that it doesn't care where it binds, which beta receptor it binds to. So it can bind to beta type 1, beta type 2, or beta type 3. And another one, and on the other hand, metoprolol is a selective for beta type 1 receptors, which means that it targets beta type 1 receptors, such as the one situated mostly in the heart and kidneys, which causes a decrease in blood pressure. Next, we have C, which is for calcium. Now, calcium is important in three actions in the cardiovascular system: contraction of vascular smooth muscle, contraction of myocytes, the muscle cells of the heart, and the conduction in the sinoatrial and atrioventricular nodes, the conduction system of the heart. Thus, decreased entry of calcium through the voltage-operated L channels produces vasodilation, decreased force of contraction, and slowing of AV conduction, which will lead to a decrease in blood pressure. So I will describe few mechanisms of how an influx or accumulation of calcium occurs, which causes the increase in blood pressure. So first we have the membrane of a myocyte, for example. Here is the extracellular fluid, the outside. And here is a G protein coupled receptor, here's a G protein, and here's a target protein. Now the target protein, we'll first look at the first mechanism which works through adenylate cyclase. And also on the cell membrane we can find the calcium channels. So when noradrenaline binds to the G protein receptor, it activates the G protein, activating the target protein, adenylate cyclase, converting ATP to cyclic AMP. Cyclic AMP then follows other enzymatic reactions, finally opening the calcium channels, basically. So here opens the calcium channels. What happens then is it allows an influx of calcium ions from the extracellular fluid to flow into the cytosol. So accumulation of these ions, these calcium ions inside the cell, increases blood pressure by a few ways, such as through contraction. So if it was a myocyte, it will contract the myocytes, and it also can, if it was a vascular smooth muscle, it contracts the vascular smooth muscle, and it also increases the conduction of the arterial ventricular nodes and the sinoatrial nodes, all which increases blood pressure. Now another way of calcium, the mechanism of calcium influxing into this inside the cell, is through a different G protein mechanism. So here again we have the cell membrane, the extracellular fluid. Here we have the G protein coupled receptor, and here we have the G protein. And instead of adenylate cyclase, we have a target protein called phospholipase C. And here is a calcium channel. So how it works is that noradrenaline binds to the G protein coupled receptor, activating the G protein, activating the phospholipase C, the target protein. And what the target protein then does is that it hydrolyzes, phosphodienosyl 4,5 biphosphate, or PIP2, converting it, basically breaking it down to two second messages, diacylglycerol and inositol triphosphate. Inositol triphosphate then binds to the receptors in the sarcoplasmic reticulum inside the cell. And when it binds to this sarcoplasmic reticulum inside the cell, the sarcoplasmic reticulum secretes calcium ions. And if calcium ions are depleted from the SR, it will send signals to the calcium channels to open up, allowing an influx of calcium ions from the outside coming inside, causing an increase in blood pressure again through contraction of the vascular smooth muscle, etc. So what calcium channel blockers do essentially is block these channels that allow the influx of calcium ions, such as this. It blocks it. Now calcium channel inhibitors usually end in pine, but not all, of course, such as Nifedipin and Felodipin. And these are selective for particular calcium channels, mainly the heart. Another type is Verapamil, and this one is non-selective, so it targets many different types of calcium channels, inhibiting it, lowering blood pressure. So no contraction, lowering blood pressure.